Welcome to Sleepless Astronomer, where we explore the wonders of space and the universe. If you're enjoying these cosmic journeys, please like this video and subscribe to the channel. We post new videos every single day, so you can tune in whenever you want to learn about the cosmos. And we'd love to hear from you in the comments. Let us know where in the world you're watching from. We always enjoy connecting with fellow space enthusiasts around the globe. Now let's begin tonight's journey through the universe. The extreme environments where life could thrive. Life on Earth exists in places that seem utterly hostile to survival. In boiling hot springs where water approaches its boiling point, in frozen Antarctic lakes where temperatures remain below zero year-round, in crushing depths of the ocean where pressure would flatten most organisms instantly, in intensely acidic pools that would dissolve metal, and in radioactive waste sites where radiation levels would kill a human in hours. These extreme environments, once thought to be sterile and lifeless, actually teem with organisms called extremophiles, life forms that not only survive but thrive in conditions that would destroy most familiar creatures. Understanding where these extremophiles live and how they manage to exist in such harsh conditions reveals that life's possibilities extend far beyond the comfortable, temperate zones we associate with habitability, suggesting that alien life might flourish in environments throughout the universe that we would never have considered searching. Temperature extremes represent one of the most dramatic challenges for life. At Yellowstone National Park and similar geothermal areas worldwide, hot springs reach temperatures near or even above the boiling point of water. In these scalding pools, organisms called thermophiles and hyperthermophiles thrive at temperatures that would cook most life forms. Some bacteria live comfortably at temperatures around 180 degrees Fahrenheit, and certain archaea, single-celled organisms distinct from bacteria, can survive and reproduce at temperatures exceeding 230 degrees Fahrenheit in superheated water under pressure that prevents it from boiling. These heat-loving organisms have specialized proteins that maintain their structure at high temperatures instead of denaturing and unfolding like normal proteins would. Their cell membranes contain special lipids that remain fluid and functional at temperatures where ordinary membranes would fall apart. Their DNA includes protective mechanisms that prevent the double helix from separating under thermal stress. Every aspect of their biochemistry has been optimized through evolution to function at temperatures that would destroy conventional life in seconds. The existence of thermophiles suggests that life could exist in hot environments throughout the solar system and beyond. In volcanic hot springs on Mars, in heated cracks near lava flows on Jupiter's moon Io, or in the scalding oceans of planets closer to their stars than Earth is to the Sun. At the opposite extreme, psychrophiles, cold-loving organisms, thrive at temperatures well below the freezing point of pure water. In Antarctica, microbes live in lakes that remain liquid beneath ice, because salt lowers the freezing point, maintaining temperatures around -5 to -20 degrees Fahrenheit. These organisms produce antifreeze proteins that prevent ice crystals from forming inside their cells, manufacture enzymes that remain flexible and functional at temperatures where normal enzymes become rigid and useless, and slow their metabolisms to conserve energy in the cold. Some bacteria found in permafrost remain viable after being frozen for hundreds of thousands of years, suggesting remarkable cold tolerance. The discovery of psychrophiles revolutionized thinking about where life could exist in the solar system. Europa, Jupiter's ice-covered moon, has a liquid ocean beneath miles of surface ice, kept liquid by tidal heating from Jupiter's gravity. The water at the bottom of this ocean, near Europa's rocky core, might be relatively warm, perhaps just above freezing, and could host psychrophilic life adapted to darkness and cold. Enceladus, Saturn's small moon, shoots geysers of liquid water through cracks in its ice shell, water that comes from a subsurface ocean. Despite the frigid surface temperature of -330 degrees Fahrenheit, the ocean beneath remains liquid, warmed by tidal forces. Life in these hidden oceans would need to tolerate extreme cold, total darkness, and high pressure, but Earth's psychrophiles prove that temperature alone doesn't preclude life. Pressure creates another extreme that life has conquered remarkably. In the Mariana Trench, the deepest part of Earth's oceans, pressure reaches about 16,000 pounds per square inch, more than 1,000 times atmospheric pressure at sea level. This crushing pressure would compress gases, alter protein structures, and collapse air-filled spaces in ordinary organisms. Yet the trench is inhabited by fish, amphipods, bacteria, and other creatures specifically adapted to extreme pressure. These organisms have no air-filled swim bladders that would collapse. Their proteins are stabilized by special amino acid sequences and by molecules called piezolites that counteract pressure's effects on molecular structure. Their cell membranes contain unsaturated fatty acids that remain fluid under pressure instead of becoming rigid. The existence of Baraful's pressure-loving organisms suggests that life could exist in the high-pressure environments found deep within planets and moons. The subsurface oceans of Europa and Enceladus experience significant pressure from the weight of overlying ice. The deeper regions of these oceans, near the rocky seafloor, would experience pressures far exceeding anything at Earth's surface. Yet if Earth organisms can adapt to pressures in the Mariana Trench, alien organisms might adapt to even higher pressures in alien oceans. Some scientists even speculate about life existing in the liquid metallic hydrogen regions deep within gas giants like Jupiter, though the extreme temperatures and pressures there would require biochemistry completely unlike anything on Earth. Acidity represents another extreme environment where life flourishes. Highly acidic environments with pH levels below 3, comparable to battery acid or stomach acid, would dissolve most biological molecules and disrupt normal cellular processes. Yet acidophiles thrive in such conditions. Iron Mountain in California hosts drainage from abandoned mines with pH levels below 0, more acidic than concentrated sulfuric acid. Despite this extreme acidity, bacteria and archaea live in these toxic streams, deriving energy from oxidizing iron and sulfur. These organisms maintain neutral pH inside their cells while existing in incredibly acidic environments, pumping protons out of their cells faster than the acidic environment can push them in, a process that requires substantial energy but allows survival in places nothing else can tolerate. At the opposite extreme, alkalophiles live in highly alkaline environments, with pH levels above 9 or even above 11. Soda lakes like Mono Lake in California and Lake Magadi in Kenya have pH levels around 10, nearly as caustic as bleach. Microorganisms in these lakes have adapted to maintain their internal chemistry despite the harsh external conditions, using specialized proteins and transport mechanisms to survive. The existence of life in both extremely acidic and extremely alkaline environments suggests that pH is a challenge life can overcome through evolution, expanding the range of potentially habitable environments to include caustic lakes and springs on other worlds. Salinity creates osmotic stress that would kill most organisms. Normal cells placed in very salty water lose water through osmosis and shrivel up. Yet halophiles, salt-loving organisms, thrive in hypersaline environments like the Dead Sea, where salt concentration exceeds 30%, and in salt evaporation ponds where salt approaches saturation. Some archaea not only tolerate but require high salt concentrations to survive. They accumulate potassium and other ions inside their cells to balance the external salt concentration, preventing osmotic water loss. Their proteins are specifically adapted to function in high salt conditions and would actually denature and unfold in normal salt concentrations. Hypersaline environments might exist on Mars, where briny water could remain liquid at temperatures below the freezing point of pure water. Salts detected on Mars's surface could create localized regions where salty water exists seasonally or sporadically. If life ever existed on Mars, or if it exists there today, it might persist in these briny environments, sheltered from the planet's coal-thin atmosphere by adaptation similar to Earth's halophiles. Radiation represents one of the most challenging extremes. Ionizing radiation damages DNA, breaks apart molecules, and creates reactive free radicals that wreak havoc on cellular chemistry. Yet radio-resistant organisms can survive radiation doses thousands of times higher than would be lethal to humans. The bacterium Deinococcus radiodurans can withstand radiation exposure of several million rads, enough to shatter its DNA into hundreds of fragments and completely repair its genome within hours, reconstituting functional chromosomes from the pieces. This organism accumulates high concentrations of manganese compounds that protect its cellular machinery from radiation damage and possesses redundant copies of its genome, along with extraordinarily efficient DNA repair mechanisms. The discovery of radio-resistant life expands possibilities for life in high radiation environments throughout the universe. Mars's surface experiences high radiation levels because Mars lacks a strong magnetic field and thick atmosphere to shield the surface from cosmic rays and solar radiation. Any surface life on Mars would need radiation resistance. The moons of Jupiter, particularly Europa, exist within Jupiter's powerful radiation belts and experience intense radiation bombardment. Life in Europa's subsurface ocean would be shielded by miles of ice, but any organism near the surface would need extreme radiation tolerance. Desiccation, extreme dryness, challenges life by removing the water necessary for biochemical reactions. Yet xerophiles can survive in nearly waterless environments. Microorganisms have been found in the driest deserts on Earth, in salt crystals, and even in the upper atmosphere. Some organisms, like tardigrades, microscopic animals also called water bears, can enter a state called cryptobiosis when they dry out. In this state, they replace water in their cells with protective molecules like trehalose sugar, essentially turning into a glass-like solid that can survive for years or decades without water, then rehydrate and resume normal activity when water becomes available again. The ability to survive desiccation suggests that life could persist in extremely dry environments like Mars, where liquid water is rare and exists only transiently. Organisms in a cryptobiotic state could wait through long dry periods, potentially centuries or longer, then reactivate during brief periods when liquid water appears. This strategy might allow life to survive, even on worlds where habitable conditions are rare and sporadic rather than continuous. Oligotrophs thrive in nutrient-poor environments where most life would starve. These organisms can extract energy and nutrients from resources that seem impossibly limited. Some bacteria derive energy from oxidizing trace amounts of hydrogen gas or from reducing tiny concentrations of metal ions. Others grow incredibly slowly, dividing perhaps once per century or even less frequently, living at the absolute minimum energy budget that can sustain life. These organisms survive in deep subsurface rocks, in ultra-pure cave water, and in nutrient-depleted ocean regions. The existence of oligotrophs suggests that life could persist in environments throughout the universe that seem too resource-poor to support metabolism. Deep beneath the surfaces of planets and moons, in the pores between rock grains, organisms might eke out existence on trace amounts of hydrogen from water-rock reactions, or on the minimal nutrients leached from minerals over geological timescales. This greatly expands the potential volume of habitable space, not just surfaces and oceans, but the entire crustal volume of rocky worlds down to depths where temperature becomes prohibitive. Some of the most extreme environments on Earth combine multiple stresses. Hydrothermal vents on the ocean floor experience high temperature, high pressure, high concentrations of toxic metals and sulfur compounds, and complete darkness. Yet these vents support thriving ecosystems based on chemosynthetic bacteria that extract energy from chemicals spewing from the vents. Hot acidic springs combine high temperature with extremely low pH. Ice-covered Antarctic lakes combine extreme cold with high salinity and seasonal or permanent darkness. Life found in these multi-stress environments proves that organisms can adapt to simultaneous challenges, not just single extremes. This ability to tolerate multiple stresses simultaneously is crucial for evaluating habitability on alien worlds, where conditions often involve several challenges at once. Europa's ocean experiences cold, pressure, darkness, and possibly high salinity, all at the same time. Mars's surface experiences extreme cold, desiccation, high radiation, and low pressure simultaneously. Venus's clouds experience high acidity, moderate temperature, and the presence of sulfuric acid droplets. Each of these environments might seem impossibly hostile when considered as a whole, but examining them as combinations of specific stresses that Earth organisms have individually overcome makes them seem more potentially habitable. The extremophiles of Earth demonstrate that life is far more flexible and resilient than once thought. Organisms have evolved mechanisms to survive and thrive in virtually every environment on Earth where liquid water exists, at least transiently, and where some source of chemical energy is available. Temperature, pressure, acidity, salinity, radiation, desiccation, each extreme that seems to represent an absolute barrier to life, turns out to be merely another challenge that evolution can overcome, given time and the right selection pressures. These discoveries transform our search for life beyond Earth. Rather than looking only for planets with Earth-like conditions, moderate temperature, neutral pH, low radiation, abundant water, we can expand our search to include extreme environments throughout the solar system and beyond. Volcanic hot springs on Mars or Venus, frozen oceans on icy moons, the clouds of Venus, subsurface aquifers deep within asteroids, the hydrothermal systems that might exist beneath the surfaces of large moons. All of these become potential habitats once we recognize that life on Earth already thrives in analogous extremes. The extreme environments where life could thrive extend from the scalding vents of volcanic springs to the frozen lakes of Antarctica, from the crushing depths of ocean trenches to the desiccated rocks of the driest deserts, from intensely acidic mine drainage to alkaline soda lakes, from the radiation-blasted rocks near nuclear waste to the nutrient-depleted waters of remote caves. Each extreme habitat on Earth hosts specialized organisms that have turned hostile conditions into homes through remarkable biochemical and physiological adaptations, proving that life's potential territory extends far beyond the comfortable middle ground to encompass nearly anywhere liquid exists, energy flows, and raw materials can be found, vastly expanding the cosmic real estate where life might emerge and flourish across the universe. The thick atmospheres of Jupiter and Saturn. Jupiter and Saturn are fundamentally different from the rocky planets of the inner solar system. They have no solid surface to stand on, no ground beneath the sky. Instead, these gas giants are essentially enormous atmospheres all the way down, layers upon layers of gas that gradually transition from thin upper hazes to dense, crushing depths, where pressure transforms hydrogen into states of matter that don't exist naturally anywhere on Earth. Understanding these thick atmospheres means understanding worlds where the atmosphere isn't just a thin shell surrounding a planet, it is the planet. The atmospheres of Jupiter and Saturn are composed primarily of hydrogen and helium, the two lightest and most abundant elements in the universe. Jupiter's atmosphere is about 90% hydrogen and 10% helium by number of molecules, with trace amounts of methane, ammonia, water vapor, and other compounds making up less than 1%. Saturn has a similar composition, though with slightly less helium, about 96% hydrogen and 3% helium, with the missing helium thought to have settled deeper into the planet's interior over billions of years. This composition mirrors the composition of the Sun and the primordial solar nebula from which the planets formed, marking these giants as worlds that captured and retained their original atmospheres from the planet-forming disk. The visible clouds we see when we look at Jupiter and Saturn exist in the uppermost layers of these atmospheres, in a region where temperatures and pressures allow various compounds to condense into droplets and crystals. On Jupiter, the highest cloud layer consists of ammonia ice crystals forming at temperatures around -150 degrees Celsius, where ammonia gas freezes into white ice. These ammonia clouds give Jupiter's zones, the bright bands that circle the planet, their brilliant white appearance. Below this ammonia layer, at slightly higher temperatures and pressures, ammonium hydrosulfide forms another cloud deck, creating brown and tan colours. Deeper still, water ice and liquid water droplets form clouds, though these are rarely visible from above, hidden beneath the overlying layers. Saturn's cloud structure is similar but more subdued. The planet appears more uniformly golden tan because a high-altitude haze of unknown composition partially obscures the underlying cloud layers. This haze may consist of complex organic molecules called tholins, created when ultraviolet light from the Sun breaks apart methane molecules in the upper atmosphere, allowing the fragments to recombine into larger, more complex hydrocarbons. These organic hazes absorb blue light and scatter red and yellow light, giving Saturn its characteristic buttery colour. The temperatures in these atmospheres change dramatically with depth. At the cloud tops, where pressure is similar to Earth's atmospheric pressure at sea level, temperatures on Jupiter hover around -145 degrees Celsius. On Saturn, they're even colder, around -180 degrees Celsius, because Saturn is nearly twice as far from the Sun and receives less solar heating. But as you descend into these atmospheres, temperatures rise rapidly. The increase comes partly from the Sun's heat that has been absorbed and transported downward, but more significantly from the planet's internal heat. Both Jupiter and Saturn emit more energy than they receive from the Sun. Jupiter radiates about 1.7 times as much energy as it absorbs from sunlight, while Saturn radiates about 1.8 times as much. This extra energy comes from the planet's interiors. Jupiter is still slowly contracting under its own gravity, a process that converts gravitational potential energy into heat through a mechanism called Kelvin-Helmholtz contraction, named after the physicists Lord Kelvin and Hermann von Helmholtz, who described this process in the 19th century. Saturn has an additional heat source. Helium is slowly separating from hydrogen in its interior and sinking toward the centre, releasing gravitational energy as it falls. Much like rain falling through Earth's atmosphere releases energy. This internal heat drives powerful convection in the atmospheres. Warm gas rises from the depths, cools as it rises and expands, then sinks back down to be heated again. This convection creates enormous circulation cells that organize the atmospheres into the distinctive banded patterns visible on both planets. Rising gas forms the bright zones, where fresh ammonia ice crystals condense and create white clouds. Sinking gas forms the darker belts, where descending motion prevents cloud formation and allows us to see deeper into the atmosphere, where darker compounds and higher temperatures exist. The winds on Jupiter and Saturn are among the strongest in the solar system. Jupiter's equatorial region rotates faster than the rest of the planet, with winds reaching speeds of about 360 kilometers per hour, roughly 225 miles per hour. Saturn's equatorial winds are even more extreme, racing along at up to 1,800 kilometers per hour, over 1,100 miles per hour, making them the fastest planetary winds in the solar system. These winds are organized into jet streams, narrow bands of fast-flowing gas that separate the zones and belts. The jet streams are remarkably stable, maintaining their positions and speeds for decades or longer. The Great Red Spot on Jupiter is perhaps the most famous atmospheric feature in the solar system. This enormous storm, large enough to swallow 2 or 3 Earths, has been observed continuously since at least 1830, and possibly as far back as the 1660s, when early telescope observers noted a large spot on Jupiter. The storm is an anticyclone, rotating counterclockwise in Jupiter's southern hemisphere, with winds at its edges reaching 400 kilometers per hour. The storm's longevity remains somewhat mysterious. On Earth, hurricanes dissipate within days or weeks when they move over land or cooler water, but the Great Red Spot has persisted for centuries. Its stability likely comes from the fact that Jupiter has no solid surface to create friction and slow the winds, and the storm may draw energy from the smaller storms it absorbs, and from the temperature difference between the warm interior and cold upper atmosphere. Saturn hosts similar, but generally smaller and shorter-lived storms. Approximately once per Saturnian year, about every 30 Earth years, a massive storm erupts in Saturn's northern hemisphere, growing to encircle the entire planet before eventually dissipating. These great white spots, as they're called, were observed in 1876, 1903, 1933, 1960, 1990, and 2010, following a remarkably regular pattern tied to Saturn's seasons. The storms appear to originate when seasonal heating destabilizes the atmosphere, allowing deep, moist convection to punch through the stable layers above and create violent thunderstorms. Lightning occurs on both Jupiter and Saturn, detected by the Voyager, Galileo, and Cassini spacecraft through radio emissions, and in some cases visible flashes. The lightning on these worlds is similar to terrestrial lightning, electrical discharges between regions of different charge within clouds, but can be far more powerful than Earth's lightning. Individual lightning bolts on Saturn have been measured at up to 1 million times more powerful than typical lightning on Earth. These storms occur in the water cloud layer, where the same process that creates thunderstorms on Earth, rising moist air forming clouds and separating electrical charges, operates on these giant planets. As you descend deeper into these atmospheres, the pressure increases relentlessly. At depths of a few hundred kilometers below the cloud tops, pressures reach thousands of times Earth's atmospheric pressure, and temperatures climb to hundreds of degrees Celsius. The atmosphere becomes denser and denser, transitioning gradually from gas to liquid, though there's no sharp boundary, no ocean surface where you suddenly plunge from air into water. Instead, the hydrogen and helium gradually become so compressed that they take on liquid properties, while still being hot enough that calling them liquid doesn't quite capture their state. They exist in a supercritical fluid state, where the distinction between gas and liquid breaks down. Descend even deeper, to depths of 10,000 to 20,000 kilometers, and pressures reach millions of times Earth's atmospheric pressure. Under these extreme conditions, hydrogen transforms into metallic hydrogen, a state of matter where the atoms are squeezed so tightly that their electrons are freed from individual atoms and flow through the material like electrons in a metal. This metallic hydrogen is thought to make up the bulk of Jupiter's mass and a significant portion of Saturn's. It's an excellent electrical conductor, and the flow of metallic hydrogen in these regions, driven by the planet's rotation and internal convection, generates the powerful magnetic fields that both planets possess. The transition from molecular hydrogen to metallic hydrogen isn't abrupt. There's a gradual change over a range of depths where hydrogen takes on increasingly metallic properties. Scientists study this transition using laboratory experiments that compress hydrogen to extreme pressures and sophisticated computer simulations that model how atoms behave under conditions impossible to fully recreate on Earth. Understanding metallic hydrogen is crucial for understanding the interiors of Jupiter and Saturn, yet its properties remain uncertain because the pressures required, several million times atmospheric pressure, can only be achieved briefly in laboratory settings. At the very centres of Jupiter and Saturn may lie rocky cores, though whether these cores exist and how large they might be remains debated. Jupiter might have a core of rock and ice, containing 10 to 20 Earth masses, or it might have no distinct core at all, just a gradual increase in the concentration of heavy elements toward the centre. Saturn might have a similar core, though perhaps smaller relative to the planet's total mass. NASA's Juno mission to Jupiter and the Cassini mission's final orbits, diving between Saturn and its rings, have provided gravity measurements precise enough to constrain the planet's interior structures, revealing that both planets have somewhat diffuse cores rather than sharp boundaries between core and envelope. The scale of these atmospheres is almost incomprehensible. On Earth, the atmosphere extends perhaps 100 kilometers before space begins. On Jupiter and Saturn, the atmosphere extends downward for thousands upon thousands of kilometers, transitioning through states from thin gas to dense supercritical fluid to liquid metallic hydrogen. If you could somehow survive the crushing pressures and searing temperatures and descend through Jupiter's atmosphere, it would take days or weeks of continuous falling to reach the planet's center, passing through layer after layer of hydrogen in different states, all of it technically atmosphere, because there's no solid surface to mark where the atmosphere ends. The study of Jupiter's and Saturn's atmospheres extends beyond academic interest. Understanding how these atmospheres work, how convection organizes into bands, how storms form and persist, how energy is transported from the interior to space, helps scientists understand atmospheric dynamics more broadly. The principles governing Jupiter's atmosphere apply, with appropriate modifications, to Saturn's atmosphere, to the atmospheres of Uranus and Neptune, and even to the atmospheres of giant exoplanets orbiting other stars. Some exoplanets, called hot Jupiters, orbit extremely close to their stars and have atmospheres heated to thousands of degrees, creating extreme versions of the processes we observe on Jupiter and Saturn. These thick atmospheres also serve as laboratories for studying hydrogen under extreme conditions. Most of the normal matter in the universe is hydrogen, and understanding how it behaves under high pressure is crucial for understanding not just giant planets, but also brown dwarfs, objects intermediate in mass between planets and stars, and the interiors of low-mass stars. The hydrogen in Jupiter and Saturn exists across a range of pressures and temperatures that spans from Earth-like conditions in the upper atmosphere to conditions approaching those in stellar interiors in the metallic hydrogen regions, providing natural experiments that inform our understanding of matter itself across a vast range of conditions. The powerful magnetic fields of dead stars. When a massive star exhausts its nuclear fuel and explodes as a supernova, the collapsing core is compressed into an object of almost incomprehensible density. A neutron star, containing more mass than the Sun, packed into a sphere only about 20 kilometers across. This violent compression doesn't just create extreme density, it also amplifies the star's magnetic field to strengths that dwarf anything found elsewhere in nature. The magnetic fields of neutron stars are among the strongest in the universe, billions or even trillions of times more powerful than Earth's magnetic field, strong enough to distort atoms, affect the fabric of empty space itself, and dominate the physics of everything near these stellar remnants. To understand how neutron stars develop such powerful magnetic fields, we need to consider what happens during the collapse. Before the supernova, the massive star had a magnetic field similar in strength to the Sun's, a few Gauss at the surface, comparable to a modest laboratory magnet. The star's magnetic field was generated by convection and rotation in its interior, creating currents of electrically conducting plasma that produced magnetism through the same basic dynamo process that generates Earth's magnetic field. When the star's core collapses, it shrinks from a radius of thousands of kilometers down to only about 10 or 12 kilometers, a compression factor of more than 1,000. As the core collapses, magnetic field lines are squeezed together. The strength of a magnetic field is proportional to the density of field lines passing through a given area, so compressing the core concentrates the field lines, amplifying the magnetic field strength enormously. The exact amplification depends on the details of the collapse, but conservation of magnetic flux, a fundamental principle stating that magnetic field lines cannot be created or destroyed, only moved around, requires that the field strength increase roughly in proportion to the decrease in the star's cross-sectional area. Shrinking the radius by a factor of 1,000 increases the magnetic field by about 1,000,000 times. A star with an initial field of 1 Gauss would emerge from collapse as a neutron star with a field of roughly 1,000,000 Gauss, or 1,000 Tesla. This is just the starting point. Most neutron stars have magnetic fields measured in hundreds of millions to trillions of Gauss. Earth's magnetic field, for comparison, measures about half a Gauss at the surface. The strongest continuous magnetic fields produced in laboratories reach around 45 Tesla, or about 500,000 Gauss, requiring enormous electromagnets and tremendous amounts of power. Yet neutron stars casually exceed these laboratory records by factors of millions or billions through nothing more than gravitational compression. Rotation adds another layer of complexity. The collapsing core spins faster as it shrinks, just as a figure skater spins faster when pulling their arms inward. Another consequence of conservation of angular momentum. A star that initially rotated once every few weeks might emerge from collapse rotating several times per second, or even hundreds of times per second. This rapid rotation, combined with the intense magnetic field, creates the phenomenon we observe as pulsars. A pulsar is a rotating neutron star whose magnetic axis is tilted relative to its rotation axis, similar to how Earth's magnetic poles don't align perfectly with the geographic poles. Charged particles near the neutron star's surface are accelerated along the magnetic field lines toward the magnetic poles, where they emit beams of radio waves, X-rays, and sometimes even gamma rays. As the neutron star rotates, these beams sweep through space like lighthouse beams. When one of the beams happens to point toward Earth, we detect a pulse of radiation. The pulses arrive with extraordinary regularity. Some pulsars keep time more accurately than the best atomic clocks over short timescales. The Crab pulsar, formed in the supernova observed in the year 1054, rotates 30 times per second and has a magnetic field estimated at around 1 trillion Gauss. This field is strong enough to do remarkable things. If you could somehow place a human body in such a field, ignoring for the moment all the other ways a neutron star would kill you, the magnetic field would be strong enough to distort your atoms. The field would force electrons into different orbital configurations, changing the chemical properties of matter and making normal biological chemistry impossible. But some neutron stars have magnetic fields even more powerful than typical pulsars. These objects, called magnetars, possess the strongest magnetic fields known in the universe, reaching 10 to the 15th Gauss, or 1,000,000,000 Tesla. These fields are so strong that they affect empty space itself. According to quantum electrodynamics, the quantum field theory describing how light and matter interact, extremely strong magnetic fields can cause the vacuum to behave in strange ways. The vacuum can become birefringent, splitting light into two beams with different polarizations, similar to how certain crystals split light. Virtual particle pairs, electrons and positrons that normally pop briefly into existence and then annihilate, can be affected by the field, altering how light propagates through the vacuum. In magnetar fields, atoms are stretched into elongated shapes, becoming needle-like structures rather than the familiar spherical electron clouds. The magnetic field overwhelms the electric forces that normally determine atomic structure, forcing electrons into highly unusual quantum states. Matter at the surface of a magnetar exists in forms never encountered anywhere else, with properties unlike any material found on Earth or in laboratory experiments. Magnetars reveal their presence through sudden outbursts of X-rays and gamma rays. The magnetic field stores enormous amounts of energy. In the strongest magnetars, the magnetic energy exceeds the binding energy holding the neutron star together, creating immense internal stresses. The neutron star's crust, composed of crystallized nuclear matter, occasionally cracks under these stresses in events called starquakes. When the crust suddenly shifts, the magnetic field lines snap and reconnect violently, releasing tremendous bursts of energy in seconds or less. The most powerful magnetar flare ever observed occurred in December 2004 from a magnetar designated SGR 1806-20, located about 50,000 light-years from Earth. In 1/10 of a second, this flare released more energy than the Sun emits in 150,000 years. The radiation from this event saturated detectors on satellites throughout the solar system and measurably affected Earth's ionosphere, despite the enormous distance. If this magnetar had been located only 10 light-years from Earth instead of 50,000 light-years away, the flare would have caused a mass extinction, stripping away the ozone layer and exposing the surface to lethal radiation. The origin of magnetar fields remains somewhat mysterious. The simple compression of the collapsing star's field cannot account for fields this strong. Magnetar fields are hundreds to thousands of times stronger than what compression alone would produce. Several theories attempt to explain the enhancement. One possibility involves a dynamo mechanism operating in the first few seconds after the neutron star forms, when the core is still extremely hot and turbulent. Convection in the proto-neutron star, combined with rapid rotation, might amplify the magnetic field through a dynamo process, similar to how Earth generates its field, but operating under extreme conditions for a brief time. Another possibility involves the formation mechanism itself. If the collapsing core rotates very rapidly, near the maximum possible rate, differential rotation between the inner and outer parts of the core might stretch and amplify magnetic field lines, winding them up like a spring and creating the immensely powerful fields observed in magnetars. This would suggest that magnetars are born from progenitor stars that were rotating particularly rapidly before collapse, or from binary star systems where mass transfer spun up the star before the supernova. The magnetic fields of neutron stars gradually decay over time. The field energy is dissipated through various processes, including emission of electromagnetic radiation and heating of the neutron star's interior. Typical pulsars with fields around 1 trillion Gauss might maintain those field strengths for millions of years. Magnetar fields, being much stronger, decay more quickly, possibly over tens of thousands of years. As magnetars age and their fields weaken, they might become ordinary pulsars indistinguishable from neutron stars that never had magnetar strength fields. This decay helps explain why magnetars are relatively rare. Astronomers have identified only about 30 confirmed magnetars in our galaxy, compared to thousands of ordinary pulsars. If magnetar fields decay on timescales of 10,000 to 100,000 years, and they form perhaps once every few hundred years in our galaxy, then at any given time, only a few dozen active magnetars would exist, which matches observations well. The magnetic fields don't just affect the neutron star itself, they extend outward into space, creating a magnetosphere. Charged particles near the neutron star cannot cross magnetic field lines easily, so they become trapped, spiraling along the field lines. The field forces these particles to co-rotate with the neutron star out to a distance called the light cylinder, where the co-rotation velocity would equal the speed of light if the field could enforce it. Beyond the light cylinder, particles can escape along the field lines, carrying energy and angular momentum away from the neutron star. This energy loss causes pulsars to gradually slow down. The Crab pulsar's rotation period increases by about 38 nanoseconds per day, as it loses rotational energy to the magnetic field and the wind of particles it drives. The rate of slowdown reveals how much energy the pulsar is radiating. Young pulsars with strong magnetic fields slow down quickly. Old pulsars with weaker fields slow down more gradually. By measuring both the rotation period and the slowdown rate, astronomers can estimate a pulsar's age and magnetic field strength. Some of the fastest spinning pulsars, called millisecond pulsars because they rotate hundreds of times per second, have much weaker magnetic fields than typical pulsars. These objects were spun up to high speeds by accreting matter from a companion star in a binary system. The infalling matter transferred angular momentum to the neutron star, spinning it up, while simultaneously burying the magnetic field under a layer of accreted material, weakening the external field. These recycled pulsars have been rejuvenated by mass transfer, given a second life as rapidly spinning objects with relatively weak fields. The study of neutron star magnetic fields connects to fundamental physics in several ways. These fields exist at strengths where quantum electrodynamics predicts effects that cannot be tested in any laboratory. Observations of magnetars and the radiation they emit provide the only way to study matter and vacuum behavior in such extreme magnetic environments. The fields also affect how nuclear matter behaves at the neutron star surface and in the crust, influencing the equation of state, the relationship between pressure and density of matter at nuclear densities and beyond. Binary systems containing two neutron stars allow even more exotic magnetic interactions. When two magnetized neutron stars orbit close together, their magnetic fields can interact, possibly reconnecting and releasing energy. As the neutron stars spiral together, driven by gravitational wave emission, the magnetic fields might play a role in the final moments before merger, potentially affecting the gravitational wave signal and the electromagnetic radiation emitted during the kilonova that follows. The powerful magnetic fields of dead stars represent nature operating at extremes impossible to recreate artificially, fields where quantum effects modify the behavior of empty space, where atoms are distorted beyond recognition, and where enough energy is stored to power the sun for millennia, all concentrated in objects small enough to fit inside a city, yet massive enough to contain more matter than an entire star. Fields that define the physics of these remarkable objects and make them among the most extreme environments existing anywhere in the cosmos. The invisible forces holding galaxies together. When you look at a photograph of a spiral galaxy, you see a beautiful pinwheel of stars, gas, and dust rotating around a central bulge. The image suggests a structure held together by visible matter, the billions of stars whose light creates the galaxy's luminous form. But appearances are deceiving. The forces actually holding galaxies together are largely invisible, operating through mechanisms both understood and mysterious. Gravity binds these cosmic structures, but most of the mass providing that gravity cannot be seen, cannot be detected except through its gravitational effects, and remains one of the deepest mysteries in astrophysics. The first clue that something invisible was holding galaxies together came from studying how stars move within them. In the 1970s, astronomer Vera Rubin conducted detailed observations of spiral galaxies, measuring the velocities of stars and gas clouds at various distances from the galactic centers. According to Newton's laws of motion and gravity, objects farther from the center of mass should orbit more slowly, just as Neptune orbits the Sun much more slowly than Mercury. The visible matter in galaxies is concentrated toward the center, with the brightness falling off dramatically in the outer regions. Based on this distribution of visible matter, stars in the outer parts of galaxies should be moving much slower than stars near the center. But that's not what Rubin found. Instead, the rotation curves, graphs showing orbital velocity versus distance from the center, were flat. Stars in the outer regions were moving just as fast as stars closer to the center, sometimes even faster. This could only mean one thing. There was far more mass in these galaxies than could be accounted for by visible stars, gas, and dust. This additional mass had to extend well beyond the visible disk, forming a massive spherical halo surrounding each galaxy. The nature of this dark matter remains unknown, but its gravitational effects are undeniable. Galaxies are embedded within dark matter halos that contain several times more mass than all the visible matter combined. A typical spiral galaxy, like the Milky Way, might contain about 100 billion solar masses of visible matter, stars, gas, dust, planets, but resides within a dark matter halo containing perhaps 1 trillion solar masses. This dark matter halo extends perhaps 10 times farther than the visible disk, creating a gravitational well that holds the galaxy together. Dark matter doesn't interact with light. It neither emits, absorbs, nor reflects electromagnetic radiation of any wavelength. It interacts with normal matter almost exclusively through gravity. This makes it invisible to telescopes, but reveals its presence through gravitational effects. The flat rotation curves that Rubin observed were the first clear evidence, but dark matter reveals itself in other ways as well. Gravitational lensing provides some of the most compelling evidence for dark matter in and around galaxies. According to Einstein's general theory of relativity, mass warps spacetime, and light follows the curves in that warped geometry. When light from a distant galaxy passes near a massive object, its path bends. By measuring this bending and calculating how much mass would be needed to produce it, astronomers can map the distribution of mass, including dark matter. These mass maps show that dark matter is distributed in huge halos around galaxies, exactly as predicted from rotation curve studies. The bullet cluster provides particularly dramatic evidence. This structure formed when two galaxy clusters collided and passed through each other. During the collision, the hot gas from each cluster, normal matter that can interact with itself, slowed down and remained near the collision site, heated by the impact. But gravitational lensing maps show that most of the mass is not where the gas is. Instead, it separated from the gas and continued moving with the galaxies themselves. This separated mass must be dark matter, which doesn't collide or interact with normal matter except through gravity, passing right through during the cluster collision. The gravitational force from dark matter operates according to Newton's law of universal gravitation for most purposes, though general relativity provides the more accurate description, especially in strong gravitational fields. The force is proportional to the product of the masses and inversely proportional to the square of the distance between them. Even though individual dark matter particles don't clump together the way atoms do, they can't radiate energy and settle into compact structures. Collectively, they form halos through gravitational attraction, with each particle orbiting in the combined gravitational field of all the others. These dark matter halos formed before the visible galaxies themselves. In the early universe, dark matter could begin collapsing into clumps earlier than normal matter, because dark matter doesn't interact with radiation. Normal matter, coupled to photons in the early universe, couldn't collapse efficiently until after recombination, when electrons combined with nuclei to form neutral atoms, and the universe became transparent. By that time, dark matter had already created gravitational wells, regions of enhanced density, and normal matter fell into these wells, forming the first galaxies within the scaffolding of dark matter structure. Computer simulations of galaxy formation must include dark matter to reproduce the observed properties of galaxies. Simulations using only normal matter produce galaxies that look nothing like what we observe. But when dark matter is included, with properties consistent with observations, non-interacting except through gravity, with a specific abundance relative to normal matter, the simulations produce galaxies remarkably similar to real ones, with flat rotation curves, realistic sizes, and appropriate clustering properties. The dark matter distribution within galaxies follows a characteristic profile. The density is highest at the center and decreases toward the outer regions, but much more gradually than the distribution of visible matter. Various mathematical models describe this distribution, with names like the NFW profile, named after Julio Navarro, Carlos Frenk, and Simon White, who studied dark matter halos in simulations in the 1990s. These profiles predict specific density distributions that can be tested against observations through rotation curves and gravitational lensing. But dark matter isn't the only force holding galaxies together. Gravity from visible matter contributes as well, though less than dark matter. The combined gravitational pull from billions of stars, gas clouds, dust, and the supermassive black hole at the center all help bind the galaxy. The distribution of this visible matter creates the gravitational potential in which stars orbit, and while dark matter dominates the total mass, the visible matter shapes the inner regions where most stars reside. Orbital mechanics plays a crucial role in keeping galaxies stable. Each star orbits in the combined gravitational field of all other matter in the galaxy, both visible and dark. Stars don't simply circle the galactic center in perfect circles like planets orbiting the Sun. Their orbits are more complex, elliptical, and tilted at various angles, creating the three-dimensional structure of the galaxy. In spiral galaxies, the disk forms because stars that were born from a rotating cloud of gas inherited that rotation, and collisions between gas particles dissipated energy and flattened the distribution into a disk. The supermassive black hole at the center of most galaxies contributes to holding the inner regions together, though its mass is typically small compared to the total galaxy mass, perhaps 0.1 to 1% of the bulge mass. The black hole at the center of the Milky Way, Sagittarius A star, contains about 4 million solar masses. While this is enormous by any terrestrial standard, it's tiny compared to the Milky Way's total mass of perhaps 1 trillion solar masses, including dark matter. The black hole's gravitational influence dominates only in the innermost few light years. Spiral density waves also play a role in galactic structure, though they're not forces holding the galaxy together in the same sense as gravity. These waves are regions of enhanced density that rotate through the disk, compressing gas and triggering star formation. The spiral arms we see are not fixed structures, with the same stars always in them, but rather patterns that rotate at a different speed than the stars themselves. Stars move in and out of the spiral arms as they orbit, spending more time in the arms where the density is higher, creating the appearance of persistent spiral structure. Galaxy clusters add another layer of complexity. Galaxies themselves are held together primarily by their dark matter halos, but galaxies cluster together in groups and clusters, which are themselves held together by even larger dark matter halos. The Milky Way is part of the local group, which includes the Andromeda Galaxy and about 50 smaller galaxies, all orbiting within a common dark matter halo. Galaxy clusters, like the Virgo cluster, contain thousands of galaxies within a massive dark matter halo containing quadrillions of solar masses. The dynamical state of galaxies, whether they're stable, expanding, or contracting, depends on the balance between kinetic and potential energy. If the kinetic energy of all the stars and gas exceeds twice the magnitude of the gravitational potential energy, the galaxy would be unbound and would eventually fly apart. The fact that galaxies remain bound over billions of years tells us that they're in virial equilibrium, a state where kinetic and potential energy are balanced according to the virial theorem. This relationship allows astronomers to estimate the total mass of galaxies from observations of how fast their contents are moving. Some alternative theories propose that dark matter doesn't exist, and that instead, our understanding of gravity needs modification. Modified Newtonian dynamics, or MOND, proposed by Mordechai Milgram in 1983, suggests that gravity behaves differently at very low accelerations, like those experienced by stars in the outer regions of galaxies. MOND can reproduce flat rotation curves without dark matter, but it struggles to explain other observations like gravitational lensing and the bullet cluster. Most physicists consider dark matter more likely to be a new type of particle rather than a modification of gravity, though the question remains open until dark matter is directly detected or conclusively ruled out. The search for dark matter particles continues in laboratories around the world. Experiments deep underground attempt to detect rare interactions between dark matter particles and normal matter. Other experiments search for signals of dark matter particles annihilating with each other or decaying into detectable particles. The Large Hadron Collider attempts to create dark matter particles in high-energy collisions. So far, no experiment has definitively detected dark matter particles, but each null result constrains the possible properties of dark matter, narrowing the possibilities. The invisible forces holding galaxies together operate on timescales of hundreds of millions to billions of years. A star near the Sun's position in the Milky Way takes about 225 million years to complete one orbit around the galactic center. During this time, the combined gravitational pull from the dark matter halo, the visible matter in the disk and bulge, and all other components keeps the star bound to the galaxy. The stability of this configuration over billions of years, galaxies don't fly apart, they maintain their structures over cosmic time, testifies to the power and precision of the gravitational forces at work. Understanding the invisible forces holding galaxies together remains one of the central challenges in astrophysics. The existence of dark matter is now accepted by most scientists based on the overwhelming gravitational evidence, but its fundamental nature remains mysterious. Whether it consists of weakly interacting massive particles, axions, primordial black holes, or something entirely unexpected, dark matter's gravitational pull provides the invisible glue that holds galaxies together, shapes their structure, determines their evolution, and creates the cosmic web of large-scale structure that defines the universe on the largest scales, making dark matter's invisibility one of the most tantalizing mysteries in science, a substance that makes up most of the universe's mass, but reveals itself only through the ancient and universal force of gravity that governs the motion of everything, from falling apples to orbiting galaxies. The solar wind that flows through space. From the surface of the Sun, an invisible river flows outward in all directions, streaming past the planets and extending far beyond the orbit of Pluto into the distant reaches of the solar system. This is the solar wind, a continuous flow of charged particles, primarily electrons and protons, that escape from the Sun's outer atmosphere and race through space at speeds ranging from 250 to over 500 miles per second. This wind carries with it pieces of the Sun itself, along with magnetic fields that thread through the solar system, creating an enormous bubble of solar influence that shapes the space environment around every planet. The story of the solar wind begins in the Sun's corona, the outermost layer of the solar atmosphere that extends millions of miles above the visible surface. The corona is paradoxically much hotter than the surface below it, while the Sun's visible surface, the photosphere, has a temperature of about 10,000 degrees Fahrenheit. The corona reaches temperatures exceeding 2 million degrees. This extreme heating, still not completely understood, but likely involving magnetic fields and wave energy, gives particles in the corona so much energy that many of them move faster than the sun's escape velocity. Imagine standing at the sun's surface and throwing a baseball upward. To escape the sun's gravity, you would need to throw it at about 380 miles per second. In the corona, thermal energy heats particles to such extreme temperatures that a significant fraction of them are moving faster than this escape velocity. These particles don't fall back to the sun, they stream away into space, carrying energy and momentum with them. The sun is essentially evaporating, losing mass continuously through this process, though at a rate so slow that it would take trillions of years to evaporate completely. The solar wind is not uniform. It flows faster from some regions of the sun than others, creating a complex structure as it expands outward. Above the sun's equatorial regions, where magnetic field lines tend to loop back to the surface, the solar wind emerges more slowly, typically around 250 miles per second. But at the sun's poles and in coronal holes, regions where magnetic field lines extend far into space, rather than looping back, the wind flows much faster, reaching speeds of 500 miles per second or more. These variations in speed create interaction regions where fast solar wind catches up to slow solar wind. Imagine cars on a highway where fast-moving traffic overtakes slower-moving traffic. The fast solar wind compresses the slow solar wind ahead of it, creating regions of enhanced density and magnetic field strength. These co-rotating interaction regions, named because they rotate with the sun as it spins, sweep through the solar system like a spiral pattern, buffeting planets with alternating streams of slow and fast wind. As the solar wind flows outward, it carries the sun's magnetic field with it. The magnetic field lines become stretched and twisted, creating a spiral pattern much like water from a rotating garden sprinkler. This interplanetary magnetic field threads through the entire solar system, connecting magnetically active regions on the sun to the distant reaches of space. When magnetic field lines from different regions of the sun come together, in space they can reconnect, releasing energy and accelerating particles to even higher speeds. The solar wind is not just a steady breeze but includes violent gusts and storms. When an eruption occurs on the sun, a solar flare or a coronal mass ejection, enormous quantities of plasma and magnetic field can be hurled into space far faster than the normal solar wind. A coronal mass ejection can contain billions of tons of material moving at speeds up to several thousand miles per second. When one of these structures reaches Earth, typically 1 to 3 days after leaving the sun, it can compress Earth's magnetic field, trigger spectacular auroras, and potentially disrupt satellites, power grids, and communication systems. The journey of a solar wind particle from the sun to Earth takes about 4 to 5 days travelling at typical speeds. During this journey, the particle encounters very little. Space between the sun and Earth is remarkably empty. A cubic inch of the solar wind near Earth contains only about 5 to 10 protons, far more tenuous than even the best vacuum we can create in laboratories on Earth. Yet despite this extreme sparseness, the solar wind carries significant momentum and energy simply because of the vast volume through which it flows and the speeds at which it travels. When the solar wind encounters a planet, what happens depends on whether that planet has a magnetic field. Earth's magnetic field creates a protective bubble called the magnetosphere that deflects most of the solar wind around the planet. The interaction is dynamic and complex. The leading edge of Earth's magnetosphere, called the bow shock, is where the supersonic solar wind first encounters Earth's magnetic field and slows down abruptly, much like air piling up in front of a supersonic aircraft creates a shock wave. This shock heats the solar wind and diverts it around Earth's magnetosphere, creating a turbulent boundary layer called the magnetosheath. some solar wind particles do manage to penetrate into Earth's magnetosphere, particularly when reconnection occurs between the interplanetary magnetic field and Earth's magnetic field. These particles get funneled along Earth's magnetic field lines toward the polar regions, where they collide with atoms in the upper atmosphere, creating the shimmering curtains of light we call auroras. The green and red colours come from oxygen atoms at different altitudes being excited by these collisions, while nitrogen produces blue and purple hues. Planets without magnetic fields like Mars and Venus experience the solar wind very differently. Without a protective magnetic bubble, the solar wind interacts directly with the upper atmosphere. Over millions of years, this interaction strips away atmospheric particles, carrying them off into space. Mars, which once had a thicker atmosphere and possibly liquid water on its surface, has lost much of its atmosphere to this process. The solar wind literally peels away the outer layers of the Martian atmosphere, particularly during strong solar storms, gradually transforming Mars from a potentially habitable world to the thin, dry atmosphere we observe today. The Moon, with neither atmosphere nor magnetic field, receives the full force of the solar wind directly on its surface. Solar wind particles impact the lunar regolith, becoming implanted in the soil. Over billions of years, this process has altered the chemistry and appearance of the lunar surface, darkening it and creating what scientists call space weathering. Ancient lunar rocks brought back by Apollo astronauts contain trapped solar wind particles that serve as a record of how the Sun's output has changed over time. Giant planets like Jupiter and Saturn have enormous magnetospheres that extend millions of miles into space. Jupiter's magnetosphere is so large that if we could see it from Earth, it would appear several times larger than the full moon in the sky. The solar wind compresses these magnetospheres on the side facing the Sun and stretches them into long tails on the night side. Within these giant magnetospheres, the interaction between the solar wind, the planet's magnetic field, and particles from the planet's moons creates some of the most intense radiation environments in the solar system. The solar wind doesn't flow forever. Far from the Sun, billions of miles beyond the orbits of the planets, it begins to slow down as it encounters the interstellar medium, the dilute gas and plasma that fills the space between stars. The Voyager spacecraft, launched in 1977, have travelled far enough to cross the boundary where the solar wind slows to subsonic speeds, called the termination shock. This boundary is not spherical, but is pushed outward in the direction the solar system is moving through the galaxy and compressed in the opposite direction. Beyond the termination shock lies a region called the heliosheath, where the solar wind has slowed but still moves outward, compressed and heated by its interaction with the interstellar medium. The exact shape and extent of this region depend on the strength of the solar wind and the pressure of the interstellar medium outside. Voyager 1 and Voyager 2 have now crossed even farther, passing through the heliopause, the outer boundary where the solar wind effectively stops and interstellar space begins. They are now in a region where the dominant flow is no longer from the Sun, but from the galaxy itself. The structure created by the solar wind, this vast bubble of solar influence, extending billions of miles in all directions, is called the heliosphere. It serves as a partial shield, deflecting some of the cosmic rays that stream through the galaxy. Without this protection, the flux of high-energy particles reaching the inner solar system would be higher, potentially affecting planetary atmospheres and creating more radiation hazards for any life on planetary surfaces. The solar wind varies with the Sun's activity cycle. During solar maximum, when the Sun is most active with many sunspots and frequent eruptions, the solar wind is stronger, more variable, and more likely to include fast-moving coronal mass ejections. During solar minimum, when the Sun is quieter, the wind becomes more regular, though still continuous. This 11-year cycle affects space weather throughout the solar system, influencing everything from auroral activity on Earth to the radiation environment encountered by spacecraft. The composition of the solar wind provides a sample of the Sun's outer layers. While predominantly hydrogen, both protons and electrons, the wind also contains helium, making up about 4% of the particles, along with trace amounts of heavier elements, like carbon, nitrogen, oxygen, neon, magnesium, silicon, and iron. These heavier elements are present in much smaller quantities but provide valuable information about solar composition and the processes occurring in the corona. Different types of solar wind have different characteristics. The slow solar wind is denser and cooler, while the fast wind is more tenuous but carries more kinetic energy due to its higher speed. Transient events like coronal mass ejections create temporary structures in the solar wind with dramatically enhanced density, speed, and magnetic field strength. These variations create a constantly changing space environment that spacecraft and planets must navigate. The solar wind also carries information outward from the Sun. Disturbances created by solar activity propagate through the solar wind, and by observing how these disturbances evolve and interact as they move through space, scientists can learn about the properties of the wind itself and the magnetic fields threading through it. Spacecraft throughout the solar system serve as sentinels, measuring the solar wind's properties at different locations and providing a three-dimensional view of how this invisible river flows through our cosmic neighborhood. Every star produces a stellar wind, analogous to our solar wind, and these winds play important roles in stellar evolution and in shaping the environments around other planetary systems. Hot, massive stars produce fierce stellar winds that can carry away significant fractions of the star's mass over its lifetime. Cool, evolved stars like red giants produce slower but denser winds. Understanding our own solar wind provides insights into these stellar winds throughout the galaxy, connecting the processes occurring in our immediate space environment to the broader evolution of stars and planetary systems across the universe. The glowing clouds, where stars are born. Scattered throughout the galaxy are vast clouds of gas and dust, some spanning hundreds of light years across, glowing with ethereal colours against the darkness of space. These nebulae are the cosmic nurseries, where stars come into being, regions where the raw materials of the universe, hydrogen and helium from the Big Bang, mixed with heavier elements forged in previous generations of stars, gather, collapse, and ignite into new points of light. Understanding these stellar nurseries means understanding one of the most fundamental processes in the cosmos, the transformation of diffuse gas into concentrated spheres of nuclear fusion that will shine for millions or billions of years. The process begins with the molecular cloud, a region of space where gas has accumulated and cooled to temperatures only a few degrees above absolute zero. These clouds are dark when viewed in visible light because the dust mixed with the gas blocks starlight from behind, creating dark patches against the background glow of the Milky Way. But observe them in infrared or radio wavelengths, and they reveal intricate structures, filaments, cores, and clumps where the density varies, creating a complex web of material threaded throughout these regions. Molecular clouds are mostly hydrogen, but at the low temperatures found within them, individual hydrogen atoms have paired up to form molecular hydrogen, H2. This molecular form is more stable at cold temperatures, and these clouds also contain molecules that might seem surprising in the depths of space: carbon monoxide, water, ammonia, formaldehyde, and even more complex organic molecules. The chemistry occurring in these cold clouds is rich and varied, with molecules forming on the surfaces of dust grains and in the gas phase, building up a diverse molecular inventory over millions of years. Something must disturb these clouds to initiate star formation. A cloud can exist in a stable state for a long time, with internal pressure from the gas supporting it against its own gravity. But if the cloud is compressed, if its density increases beyond a critical threshold, gravity begins to win. This compression can come from several sources: a shockwave from a nearby supernova explosion pushing through space, the compression created when spiral arms of the galaxy pass through the region, or even the radiation and winds from existing massive stars that can trigger collapse in adjacent cloud material. Once collapse begins, the cloud fragments into smaller pieces. A single large molecular cloud doesn't collapse into one giant star. Instead, it breaks apart into hundreds or thousands of individual collapsing cores, each one potentially forming a star or a small system of stars. This fragmentation occurs because as the cloud collapses, it develops instabilities. Regions that are slightly denser collapse a bit faster, pulling in material from their surroundings, and these growing density enhancements become the seeds of individual stars. Picture one of these collapsing cores. Initially, it might be 1/10 of a light year across, containing perhaps a few times the mass of our Sun, with a density barely above that of the surrounding cloud. As it contracts under its own gravity, the material falls inward, but it doesn't fall uniformly. The core rotates slowly, inherited from the overall rotation of the cloud, and as it contracts, conservation of angular momentum causes it to spin faster, just as a figure skater spins faster when pulling their arms inward. This rotation prevents all the material from falling directly onto the forming star at the center. Instead, material settles into a rotating disk around the protostar, a flattened structure where gas and dust orbit the central condensation. This is a protoplanetary disk, the structure from which planets will eventually form. The material in this disk gradually spirals inward, losing angular momentum through viscosity and magnetic effects, feeding the growing protostar at the center, while the outer portions of the disk may remain in orbit for millions of years. As the protostar grows, accumulating more and more mass from the infalling material, its center heats up. Gravitational potential energy converts to thermal energy as material falls inward, and the temperature and pressure at the core climb steadily. The protostar begins to glow, first emitting infrared radiation, then gradually becoming brighter as it contracts. At this stage, it's not yet a true star. No nuclear fusion occurs at its core, but it's radiating energy produced by gravitational contraction, a process called Kelvin-Helmholtz contraction. The infalling material doesn't simply accumulate smoothly. Young protostars are violent, turbulent objects. They generate powerful magnetic fields that interact with the surrounding disk and the infalling gas. These magnetic fields can launch jets, narrow streams of gas that shoot outward from the poles of the protostar at speeds of hundreds of miles per second. These jets plow into the surrounding molecular cloud, creating bow shocks where they collide with the ambient gas, heating it and causing it to glow. These glowing regions, called Herbig-Haro objects, appear as bright knots and filaments near young stars, moving visibly over periods of years as the jets evolve and push through the surrounding gas. The jets serve an important function. They carry away angular momentum and energy, allowing material in the disk to continue falling onto the protostar. Without this mechanism to remove angular momentum, the disk would simply spin faster and faster, and accretion would halt. The protostar continues to accrete material and contract for hundreds of thousands to millions of years, depending on its mass. During this time, it's deeply embedded in the cloud that spawned it, hidden from view at visible wavelengths by the cocoon of gas and dust surrounding it. Infrared observations can penetrate this obscuration, revealing the glowing protostar and its disk within the dark cloud. These embedded protostars mark the earliest visible stages of star formation, objects that are still gaining mass and have not yet ignited nuclear fusion. Eventually, the temperature and pressure at the protostar's core reach a critical threshold, typically around 10 million degrees. At this point, protons begin to fuse, creating helium and releasing energy through nuclear fusion. The protostar becomes a true star, entering what's called the main sequence, where it will spend the majority of its life fusing hydrogen into helium. The energy released by fusion creates an outward pressure that finally halts the gravitational contraction, and the star settles into a stable configuration where gravity and pressure are balanced. When the star ignites, it begins to affect its surroundings dramatically. The radiation from the young star heats the surrounding gas and dust. Ultraviolet light from the star ionizes hydrogen atoms, stripping electrons away and creating a region of ionized gas called an H2 region. These ionized regions glow with a characteristic reddish-pink color, the result of electrons recombining with protons and cascading down through energy levels, emitting light at specific wavelengths. This is the glow we see in many famous nebulae: the Orion Nebula, the Eagle Nebula, the Lagoon Nebula, vast regions of ionized gas illuminated by the intense radiation from young hot stars. If the star is particularly massive and hot, more than about 8 times the Sun's mass, it produces copious ultraviolet radiation that can ionize gas over large volumes of space. A single massive star can create an H2 region spanning dozens of light years. Multiple massive stars forming in the same region create even larger ionized bubbles. The Orion Nebula, visible to the naked eye as a fuzzy patch in Orion's sword, glows because of a handful of massive young stars at its center, whose radiation ionizes the surrounding molecular cloud. The radiation pressure and stellar winds from young stars don't just make the cloud glow, they also begin to push the gas away, clearing out cavities in the molecular cloud. This feedback can actually trigger more star formation in the surrounding material. As the expanding HII region compresses gas at its edges, it can push that material above the density threshold needed for collapse, triggering new rounds of star formation in a process that propagates through the cloud. Young star clusters often show evidence of sequential star formation, with the oldest stars at the center surrounded by progressively younger stars farther out. The initial generation of stars alters the cloud, compressing and heating gas at the periphery, triggering the formation of the next generation. This process continues until the cloud is either dispersed entirely by the radiation and winds from the young stars, or exhausted of material dense enough to form new stars. The most massive stars, those dozens of times more massive than the Sun, live brief but spectacular lives. They burn through their nuclear fuel in just a few million years, and then explode as supernova, catastrophic events that briefly outshine entire galaxies. These explosions inject tremendous energy into the surrounding gas, heating it to millions of degrees, accelerating it to thousands of miles per second, and enriching it with heavy elements created in the star and in the supernova explosion itself. Carbon, oxygen, silicon, iron, and even heavier elements like gold and uranium. These heavy elements mix into the molecular cloud, changing its composition. The next generation of stars that forms from this enriched material will contain more heavy elements than the previous generation. This process of stellar birth, life, death, and rebirth has been occurring for over 13 billion years, gradually enriching the interstellar medium with heavy elements. The earliest stars in the universe formed from nearly pure hydrogen and helium. Stars forming today, including our Sun, contain about 2% heavy elements by mass, a small fraction, but crucial for the formation of planets, and ultimately for the existence of life. The dust mixed throughout these star-forming clouds plays a crucial role beyond just blocking light. The tiny grains, typically less than a micrometer in size, serve as surfaces where molecules can form. Hydrogen atoms landing on a grain's surface can find each other and bond, forming molecular hydrogen far more efficiently than they could in the gas phase. Water molecules, carbon monoxide, and more complex organics also form on grained surfaces, then evaporate back into the gas or become incorporated into forming stars and planets. Star formation is not perfectly efficient. Only a small fraction of the gas in a molecular cloud, perhaps 1 to 10%, actually ends up in stars. The rest is either dispersed by stellar feedback, ejected by stellar winds and supernova explosions, or simply never reaches densities high enough to collapse. The molecular clouds we observe are continuously evolving, with some regions collapsing to form stars while other regions are being cleared out by the very stars that recently formed within them. Different regions of the galaxy have different rates of star formation. The spiral arms, where gas is compressed as it enters these density waves, show enhanced star formation, lighting up with the blue glow of young hot stars and the red emission from H2I regions. The galactic center, with its extreme environment and powerful tidal forces, has intense star formation, but also extreme feedback that can suppress star formation. The outer regions of the galaxy, with less gas available, form stars more slowly. Star formation is occurring right now throughout the Milky Way and throughout the universe. In distant galaxies, billions of light years away, we observe intense starbursts where entire regions of galaxies are forming stars at rates thousands of times higher than in our galaxy, triggered by galaxy collisions or mergers that compress enormous quantities of gas. The stars forming in those distant galaxies emit light that has travelled across most of the universe's history to reach our telescopes, showing us star formation as it occurred when the universe was much younger. The glowing nebulae we see in telescopes and photographs are not static monuments, but dynamic regions of ongoing transformation. The clouds are collapsing, the protostars are growing, the newly formed stars are dispersing the clouds that gave them birth. Within a few million years, the blink of an eye on cosmic timescales, a star-forming region transforms from a dark molecular cloud to a bright cluster of young stars, to a dispersed association of stars gradually spreading through the galaxy, each one carrying forward the legacy of its birth, enriching future generations of clouds with the elements created during its life, continuing the cycle of stellar birth and death that has shaped the galaxy since its formation billions of years ago. The zone where life could exist. Life as we know it requires certain conditions to exist. Too hot, and water boils away. Too cold, and water freezes solid. Without liquid water, life as we understand it cannot survive, at least not the kind of carbon-based, water-dependent life that evolved on Earth. This simple requirement creates a critical region around every star called the habitable zone, sometimes nicknamed the Goldilocks zone, because conditions there are neither too hot nor too cold, but just right for liquid water to exist on a planet's surface. Understanding this zone and what makes it special reveals both the requirements for life and the astonishing variety of places in the universe where life might possibly emerge. The habitable zone is not a single precise distance from a star, but rather a range of distances, a band extending outward from the star where temperatures allow water to remain liquid. For our Sun, this zone extends roughly from about 90 million kilometers to about 150 million kilometers from the Sun. Earth, orbiting at about 150 million kilometers, sits comfortably within this zone, though closer to the inner edge than the middle. Venus, at about 108 million kilometers, orbits just inside the inner edge, where temperatures are too high. Its surface temperature exceeds 450 degrees Celsius, hot enough to melt lead, far too hot for liquid water. Mars, at about 230 million kilometers, orbits near or just beyond the outer edge, where temperatures are generally too cold. Though liquid water might occasionally exist in certain locations under special conditions. The boundaries of the habitable zone depend entirely on the star's properties. hotter, brighter stars have habitable zones located farther out because their intense radiation heats planets to higher temperatures. Cooler, dimmer stars have habitable zones located much closer in. A red dwarf star, the most common type of star in the galaxy, might be only 1/10 as luminous as the Sun, meaning its habitable zone would be about 1/3 the distance from the star. A planet orbiting in the habitable zone of a red dwarf might orbit only 10 million kilometers from its star, closer than Mercury orbits our Sun, yet still maintain temperatures suitable for liquid water because the star is so much dimmer. The habitable zone also depends on the planet's atmosphere. A thick atmosphere with greenhouse gases can trap heat and keep a planet warm even if it orbits farther from its star than the outer edge of the simple, habitable zone. Venus demonstrates the opposite effect. Its extremely thick carbon dioxide atmosphere creates a runaway greenhouse effect, trapping heat so efficiently that surface temperatures soar far beyond what you would expect from Venus's distance from the Sun alone. Without this greenhouse effect, Venus might be cool enough for liquid water. With it, the planet is an inferno. Mars provides another instructive example. Mars orbits near the outer edge of the Sun's habitable zone, and its thin atmosphere, less than 1% the pressure of Earth's atmosphere, cannot retain much heat. Surface temperatures average around -60 degrees Celsius, far too cold for liquid water most of the time. But billions of years ago, Mars had a thicker atmosphere and likely had liquid water flowing on its surface, creating the river valleys and lake beds that spacecraft have photographed. Mars lost most of its atmosphere over time, probably because its weak magnetic field couldn't protect the atmosphere from being stripped away by the solar wind. The planet moved out of effective habitability not by changing its orbit, but by losing the atmosphere that kept it warm. Earth maintains liquid water on its surface through a fortunate combination of factors. Our distance from the Sun provides a baseline amount of heating. Our atmosphere, with modest amounts of carbon dioxide and water vapor, acting as greenhouse gases, traps enough heat to raise the surface temperature by about 33 degrees Celsius, above what it would be without an atmosphere. Our magnetic field, generated by the liquid iron core's motion, shields the atmosphere from the solar wind, preventing the atmospheric loss that doomed Mars. Our planet's size gives it enough gravity to hold onto its atmosphere over billions of years. But the habitable zone is more complex than just distance from a star and atmospheric composition. Other factors influence whether life could actually emerge and survive. Planetary mass matters. A planet too small cannot retain an atmosphere because its weak gravity allows atmospheric gases to escape to space. A planet too large might have such a thick atmosphere that surface pressures become extreme, or might retain so much hydrogen and helium from its formation that it becomes more like a miniature gas giant than a terrestrial world. The planet's rotation rate influences habitability as well. A planet that rotates very slowly, or is tidally locked to its star, showing the same face always toward the star as the Moon does to Earth, would have extreme temperature differences between the permanent day side and permanent night side. The day side might be too hot for liquid water, while the night side freezes. Venus rotates extremely slowly, taking more than 200 Earth days to complete one rotation, though its thick atmosphere distributes heat efficiently enough that temperatures are fairly uniform across the planet, despite this slow rotation. Stellar variability affects the habitable zone's stability over time. The Sun's luminosity has increased by about 30% over its lifetime. Early in Earth's history, when the Sun was dimmer, Earth received less heat. Yet geological evidence shows that liquid water existed on Earth's surface going back nearly 4 billion years, despite the fainter Sun. This is called the faint young Sun paradox. The solution probably involves a thicker atmosphere with more greenhouse gases in Earth's past, compensating for the dimmer Sun and keeping temperatures warm enough for liquid water. As stars age, their habitable zones move outward. The sun will continue brightening over the next billion years or so. Eventually, perhaps in 1 billion to 1.5 billion years, the sun will become bright enough that even with our current atmosphere, Earth's surface will become too hot for liquid water. The oceans will evaporate, water vapor will accumulate in the atmosphere, and the increased greenhouse effect will push temperatures even higher in a runaway process. Earth will exit the habitable zone, not because Earth moves, but because the habitable zone moves outward as the sun brightens. Subsurface habitability expands the possibilities beyond the traditional habitable zone. Moons orbiting gas giant planets can have liquid water beneath their icy surfaces, even if they orbit well outside the star's habitable zone. Jupiter's moon, Europa, and Saturn's moon, Enceladus, both have subsurface oceans kept liquid by tidal heating, the gravitational squeezing from their parent planets that generates internal heat. These moons demonstrate that life might not require surface liquid water or even a planet within the traditional habitable zone. The requirements might simply be liquid water somewhere, an energy source, and the right chemical ingredients. Tidal heating expands the possible locations for life significantly. A planet or moon doesn't need to orbit at a specific distance from its star if internal heat from tidal forces can keep subsurface water liquid. This might be particularly important for moons orbiting planets in the habitable zones of red dwarf stars, where tidal locking to the star might make surface habitability challenging, but subsurface oceans remain possible. The chemical composition of the planet matters as much as its location. Life requires more than just water. It needs raw materials. Carbon, nitrogen, phosphorus, sulfur, and trace amounts of many other elements are essential for the biochemistry we know. Planets that form too close to their star might lack volatile elements like carbon and nitrogen that are essential for life. Planets that form too far out and then migrate inward might have compositions dominated by ices, rather than having the right balance of rock, metal, water, and organics. Stellar type influences habitability in ways beyond just temperature. Red dwarf stars, while having habitable zones close in, pose challenges for life. These stars frequently produce powerful flares, sudden bursts of radiation, and charged particles that could strip away planetary atmospheres and damage biological molecules. A planet in the habitable zone of a red dwarf would need a strong magnetic field to protect against this radiation. Additionally, red dwarfs are so dim that their habitable zone planets likely become tidally locked, always showing the same face to the star, which creates the extreme temperature contrast problem. More massive stars, while having habitable zones farther out, present a different problem. They burn through their fuel quickly and don't live long enough for complex life to evolve. A star twice the sun's mass might only live a few billion years before exhausting its hydrogen fuel and evolving into a red giant. On Earth, simple life emerged fairly quickly, within the first billion years, but complex multicellular life took nearly 3 billion years to appear. More massive stars might not remain stable long enough for complex life to evolve on their planets. Binary star systems where two stars orbit each other create more complicated habitable zones. If the stars orbit close together, planets might orbit far enough from both stars that the pair acts like a single brighter star, creating a habitable zone at a large distance. If the stars are widely separated, planets might orbit just one star in a habitable zone, determined primarily by that star's properties. But intermediate cases, where the stars are separated by distances comparable to their habitable zones, create complex and potentially unstable conditions for planets. The galactic habitable zone adds another layer of consideration. Different regions of the galaxy have different properties relevant to life. Near the galactic center, stars are packed more densely, and supernova explosions occur more frequently, potentially sterilizing planets with intense radiation. Far in the outer reaches of the galaxy, stars might be too poor in heavy elements to form rocky planets with the chemical complexity needed for life. The region where our Sun orbits, about halfway out in the galactic disk, might represent a galactic habitable zone where conditions are most favourable for life to emerge and survive long term. Exoplanet discoveries have found thousands of planets, many within their stars' habitable zones. Proxima Centauri b, orbiting the nearest star to our Sun, sits within its star's habitable zone, though whether it actually has liquid water and a protective atmosphere remains unknown. Kepler and other missions have found dozens of roughly Earth-sized planets in habitable zones, though determining which of these might actually host life requires detailed atmospheric studies that current telescopes can barely begin to perform. The concept of habitability continues evolving as we learn more about the diversity of planetary environments. Life might exist in forms very different from Earth's biology, adapted to environments we would consider extreme. Subsurface oceans beneath ice shells, atmospheres of exotic chemistry on planets very different from Earth, even clouds in the atmospheres of gas giants. All these represent potential habitats that expand the zone where life might exist far beyond the simple band of distance where liquid water exists on a planet's surface. The habitable zone represents our best current understanding of where to look for life, based on the one example we have: Earth. It's a starting point, a place to begin the search, knowing that life's possibilities might extend far beyond this simple definition. The zone where life could exist might be much larger than we imagine, encompassing not just planets at the right distance from their stars, but moons with tidal heating, planets with exotic chemistries, and environments we haven't yet conceived, each one a potential home for biology waiting to be discovered. What alien oceans might contain? Earth's oceans are vast, salty bodies of liquid water covering more than 70% of the planet's surface, containing dissolved minerals, organic molecules, and a staggering diversity of life, from microscopic bacteria to the largest animals that have ever existed. But oceans on other worlds might be fundamentally different, not just in what organisms inhabit them, but in their very composition, what liquids fill them, what chemicals dissolve in those liquids, and what physical conditions prevail at their depths. Understanding what alien oceans might contain means considering not only water-based oceans with different chemistry than Earth's seas, but entirely different liquids that could serve as oceanic solvents on worlds with radically different temperatures, pressures, and geological histories. The most familiar alien oceans would be water-based oceans on other worlds. Several candidates exist in our own solar system. Europa, Jupiter's ice-covered moon, harbours a global ocean containing perhaps twice as much liquid water as all of Earth's oceans combined, kept liquid by tidal heating from Jupiter's gravity despite surface temperatures around -160 degrees Celsius. This ocean lies beneath an ice shell estimated to be 15 to 25 kilometers thick, shielding the water from the vacuum of space and from Jupiter's intense radiation belts. What Europa's ocean contains remains unknown, but scientific models and the limited data from spacecraft flybys provide clues. The ocean is certainly salty, likely containing dissolved salts leached from Europa's rocky seafloor over billions of years. Magnesium sulfate, sodium chloride, and other salts detected spectroscopically in Europa's ice shell probably came from the ocean below. The salinity might be similar to Earth's oceans, or it might be substantially higher, creating a briny sea where salt concentrations affect water's freezing point, density, and chemistry. High salinity would influence what kinds of life could potentially evolve, favouring organisms with mechanisms to cope with osmotic stress. The ocean would be dark. Absolutely no sunlight penetrates through kilometres of ice. Any life in Europa's ocean would depend on chemical energy rather than photosynthesis. The rocky seafloor, might host hydrothermal vents similar to those on Earth's ocean floor, where hot, mineral-rich water spews from cracks in the rock, driven by volcanic heat from the Moon's interior. These vents could provide energy and nutrients to support chemosynthetic bacteria that extract energy from chemicals in the vent fluids: hydrogen, methane, hydrogen sulfide, iron compounds. If such microbes exist, they might form the base of a food chain, supporting more complex organisms analogous to the tube worms, clams, and crustaceans that cluster around Earth's hydrothermal vents. Dissolved gases would be present in Europa's ocean: carbon dioxide from reactions between water and rock, hydrogen from water-rock reactions, and possibly from radiolysis, where radiation breaks apart water molecules near the ice-ocean boundary, methane from geological processes, or potentially from biological activity. The concentrations and ratios of these gases would reveal much about the ocean's chemistry and whether biological processes might be occurring. Organic molecules, carbon-based compounds, almost certainly exist in Europa's ocean. Comets and meteorites containing organic compounds have bombarded Europa throughout its history. Chemical reactions between water and rock produce simple organic molecules. If life exists, it would produce far more complex organic molecules: amino acids, lipids, sugars, proteins. Detecting complex organic molecules in samples from Europa's ocean would be strong evidence for biology, though distinguishing biological from non-biological organic chemistry would require careful analysis. Enceladus, Saturn's small moon, provides an even more accessible alien ocean because it actively vents ocean water into space through cracks in its south polar ice shell. The Cassini spacecraft flew through these plumes, analysing their composition directly. The plumes contain water vapour, ice grains, carbon dioxide, methane, ammonia, molecular hydrogen, and complex organic molecules, including some with chains of carbon atoms, ingredients that on Earth would suggest habitability. The presence of molecular hydrogen is particularly intriguing because it suggests water-rock reactions at high temperatures, consistent with hydrothermal vents on Enceladus's seafloor. The organic molecules, while not proof of life, show that organic chemistry is occurring in Enceladus's ocean. Titan, Saturn's largest moon, presents an entirely different type of ocean, not water, but liquid hydrocarbons. Titan's surface temperature hovers around -180 degrees Celsius, far too cold for liquid water, which is frozen as hard as rock. But at these temperatures, methane and ethane exist as liquids. Titan has lakes and seas of liquid hydrocarbons near its poles, bodies of liquid methane and ethane with dissolved propane, butane, nitrogen, and traces of more complex organic molecules. These hydrocarbon seas are hundreds of meters deep in some places, creating environments completely unlike anything on Earth. What Titan's hydrocarbon oceans might contain depends on what chemistry can occur in liquid methane at cryogenic temperatures. Organic chemistry certainly happens. Titan's atmosphere produces complex organic molecules through photochemistry, and these molecules rain down onto the surface, accumulating in the lakes and seas. Nitrogen compounds, cyclic molecules, long-chain hydrocarbons, and possibly even more complex molecules might dissolve in the methane. Whether life could exist in liquid methane remains highly speculative, but if it does, it would use completely different biochemistry than Earth life, perhaps with cell membranes made from molecules that are insoluble in hydrocarbons rather than the water-soluble membranes Earth organisms use. Titan also likely has a subsurface water ocean beneath its icy crust, similar to Europa and Enceladus. This buried ocean would be separate from the surface hydrocarbon seas, creating the possibility that Titan might host two completely different types of chemistry: water-based chemistry in the deep subsurface ocean and hydrocarbon-based chemistry in the surface seas. Whether these two environments could both support life, and whether life in one could be related to life in the other represents one of the most intriguing questions about this remarkable moon. Ammonia oceans represent another possibility for alien seas. Ammonia remains liquid at temperatures between -77 and -33 degrees Celsius at Earth atmospheric pressure, colder than water but warmer than methane. A planet or moon with temperatures in this range might have oceans of liquid ammonia or ammonia-water mixtures. Pure ammonia is a less effective solvent than water for many compounds, but it can dissolve different substances than water, creating entirely different ocean chemistry. An ammonia ocean would be less dense than water ice, so ammonia ice would sink rather than float, potentially affecting planetary heat transport and ocean circulation. The ocean's pH would be highly alkaline. Ammonia is a base, creating chemistry very different from Earth's near-neutral oceans. Organisms adapted to ammonia oceans would need biochemistry that functions at low temperatures and high pH, potentially using ammonia molecules in ways analogous to how Earth life uses water. Sulfuric acid oceans sound implausible, yet Venus's clouds contain concentrated sulfuric acid droplets, and some scientists have speculated about life existing in these droplets. While Venus's surface is hellishly hot, the cloud layers at altitudes of 50 to 60 kilometers above the surface have temperatures around room temperature, quite comfortable by terrestrial standards. If life could exist as airborne organisms living in cloud droplets, those droplets would be concentrated sulfuric acid, requiring biochemistry completely unlike anything on Earth. Certain Earth microbes can tolerate extremely acidic conditions, proving that acid-resistant biochemistry is possible. But whether life could actually live in sulfuric acid remains unknown and highly controversial. Silicate oceans, molten rock, might exist on lava worlds orbiting extremely close to their stars. At temperatures exceeding 2000 degrees Celsius, rock melts into liquid magma that flows like water. While most scientists consider molten rock too hot and destructive for any conceivable biochemistry, some speculative theories propose exotic life forms based on completely different chemistry that might exist in magma, perhaps using silicate molecules or metal compounds as structural materials instead of carbon-based organic molecules. Such life would be so alien that we might not recognize it as life, even if we observed it directly. Supercritical oceans exist under conditions where temperature and pressure are high enough that the distinction between liquid and gas breaks down. Supercritical water, existing at temperatures above 374 degrees Celsius and pressures above 220 atmospheres, has properties intermediate between liquid and gas. Deep beneath the surfaces of massive ocean worlds, pressures might be high enough to create supercritical water oceans. The chemistry in supercritical water differs dramatically from normal water chemistry, with different solubilities, reaction rates, and molecular interactions. Whether life could adapt to supercritical conditions remains unknown, but the possibility can't be ruled out for extremely exotic organisms. The ocean floor composition profoundly affects ocean chemistry. Earth's ocean floors are basaltic rock, and water-rock interactions continuously cycle elements between the ocean and the crust. Alien ocean floors might be different, perhaps pure ice if the ocean is deep enough that high-pressure ice forms at the bottom, or perhaps carbonate rocks, serpentinite, or other minerals depending on the planet's composition. These different minerals would leach different elements into the ocean, creating different dissolved chemistry. Hydrothermal vents on alien seafloors might vent fluids with very different composition than Earth's vents. On Europa or Enceladus, where the rocky interiors might be rich in different minerals than Earth's mantle, vent fluids might contain unusual concentrations of metals, sulfur compounds, or other chemicals. These different chemistries would favour different types of chemosynthetic organisms if life exists, potentially creating ecosystems with no analogue on Earth. Dissolved oxygen would be rare or absent in most alien oceans unless photosynthetic life has evolved and produced oxygen for billions of years as on Earth. Most alien oceans would be anoxic, without dissolved oxygen, more similar to Earth's oceans before the Great Oxidation Event 2.5 billion years ago. Anoxic oceans contain different dissolved metals and have different chemistry than oxygenated oceans. Iron remains dissolved in anoxic water instead of precipitating as rust. Sulfur chemistry dominates, rather than oxygen chemistry. Life in anoxic alien oceans would use anaerobic metabolism, extracting energy from reactions that don't involve oxygen. Temperature gradients in alien oceans depend on heat sources. Earth's oceans are heated from above by sunlight and from below by geothermal heat, creating complex circulation patterns. Europa's ocean, heated only from below by tidal heating and with a cold ice ceiling above, might have upside-down circulation compared to Earth. Warm water rising from the seafloor toward the ice ceiling where it cools and sinks back down. These circulation patterns would affect nutrient distribution, temperature zones, and where life might be most abundant. Pressure increases with depth in any ocean, but the rate depends on the liquid's density and the world's gravity. Europa's ocean might reach pressures exceeding 10,000 atmospheres at the seafloor, much higher than Earth's deepest ocean trenches due to the ocean's great depth. Organisms adapted to such extreme pressure would have specialized biochemistry that functions under conditions where molecules are compressed and reaction rates are altered by pressure's effects on molecular structure. Seasonal variations might affect some alien oceans. A planet with significant axial tilt would experience seasonal changes in star heating that could affect surface ocean temperatures, causing seasonal mixing, ice formation and melting, and biological cycles tied to seasons. Tidally locked planets would have no seasonal variations, but might have temperature zones related to distance from the substellar point, the location where the star is directly overhead, creating warm equatorial regions and cold polar regions with different ocean chemistry in each zone. Ice-covered oceans might have ecosystems concentrated near the ice-water boundary, where any photosynthesis using radiation penetrating through cracks in the ice could occur, or where chemical gradients between the ice and deep ocean creates energy harvesting opportunities. Life might cluster in cracks and crevices in the ice ceiling, or in regions where the ice is thinnest and most likely to crack or melt. What alien oceans might contain ranges from the familiar, salty water with dissolved minerals and potentially abundant life, to the exotic, liquid methane seas with dissolved organic compounds, ammonia oceans at cryogenic temperatures, supercritical fluids blurring the line between liquid and gas, even molten silicate magmas on scorching hot worlds. Each ocean's composition reflects its world's temperature, pressure, geology, and history, creating environments where chemistry operates under different rules, where life, if it exists, would be adapted to conditions we can barely imagine, where exploration by future spacecraft might reveal ecosystems as diverse and wondrous as Earth's oceans, or so alien that we struggle to recognize biology when we see it, expanding the inventory of habitable environments to include not just Earth-like water oceans, but any stable liquid where dissolved chemicals, energy sources, and sufficient time might allow chemistry to evolve into biology beneath the waves of alien seas scattered across the solar system and beyond.